So I'm Stefanos. I'm mainly working on the intersection of programming languages and computer security, and mainly focusing on blockchain security, and the last few years on zkSecurity. This work is a joint work with Jens, David Theodore, David Wong, Mohammad, and Ben. So I will start by giving a brief overview of what is the state of ZKP applications. So we have ZK rollups, which are layer 2 scalability solutions for legacy blockchains like Ethereum and Bitcoin. And the idea is that users submit transactions to a layer 2 blockchain that is much more lightweight. The layer 2 nodes get the transactions, batch them together in a single batch, and then producing a proof of correct execution for those transactions, and then submitting that proof to an L1 and then verify the correctness of the execution. And currently, ZK rollups handle more than $5 billion, and it's the main application we see in production in the blockchain world. Another pioneering application is zkSecurity, which is basically private blockchain. It still has a pretty large market cap. And then we have what we call them ZK apps. One example is ZK login, which is a similar idea with the regex example we saw previously. And the idea is to use basically JWT providers like Google and execute transactions in the Sui blockchain using your authentication mechanism from Web 2 applications. And there are many more applications. But so far, what we haven't seen in the space is any major exploit of any of those protocols. And interestingly, there were major critical vulnerabilities in many of those applications in production. So Zcash had a vulnerability since the first release, and people that were working on Zcash identified that vulnerability a few years later. No one had exploited. Then Tornado Cash had a major vulnerability that was identified by a white hat hacker, and then they fixed it. Lately, ZK rollups have huge bug bounty programs, and security researchers have managed to find vulnerabilities and get bounties that worth more than some millions of dollars. And then in every protocol in that space, before deploying it, we are doing security audits, and typically in those security audits, you can find a few critical vulnerabilities. And also the ratio of critical vulnerabilities is even higher than traditional blockchain applications. So the main two hypotheses that people having about why we don't have any exploits so far is either that there is not enough return of investment for attackers, which I don't think it's true anymore. And secondly, that ZK programs and ZK circuits are very complicated and not many people can understand them, let alone to exploit them. But I would say that this is also not true anymore. There are a lot of learning resources, and for example, here is the underlying vulnerability in the Tornado Cash contracts that if someone could have exploited, could have drained the complete, all the funds in Tornado Cash. And anyone that has written a circumcircuit can see that it's a pretty trivial error. So people could have found it if that happened today. So I will continue with a brief overview of the main properties that someone might want to use when deploying a ZKP. We have knowledge soundness, which means that a dishonest prover cannot convince the verifier of an invalid statement. We have perfect completeness, which means that we can always produce a proof for valid statements and verify these proofs. And we have zero knowledge, which means that the proof that reveals nothing about the private part of our computation or of our statement. So an attacker might try to exploit any of those properties. And the most critical one in most protocols is the soundness property. So what an attacker can try to do is to produce a proof that will surpass the checks that the verifier performs and will be able to, for example, in the Tornado Cash or in the Zcash example, to get a lot of money out of those systems. So we identified three main adversaries. The first one is a network adversary that can just observe the system, so it cannot interact with the system. The second adversary is an adversarial user that can submit inputs to some provers that will then generate the proofs. And here we can say that we trust that the prover is an honest participant in our protocol. And the third one, which is the most important one, is that the adversary has the ability to produce proofs and submit proofs in order to try to exploit some vulnerabilities. Most protocols that are in production actually currently have the adversarial user thread model, but all of them planning to go and be completely permissionless and trustless. So we want to focus on the third one. So in this work, we analyzed 141 bugs, mainly from audit reports, vulnerability disclosures, and bug trackers. And we did not focus in any non-ZKP related vulnerabilities. So the first thing we did was to try to understand what are the different layers in those systems and how those layers interact and what can go wrong in each layer. So we start with one relation that we want to prove. You can think of it as a program, as some specification or whatever, and then we have some public inputs and maybe some private inputs. The first step is to write a circuit, which is a manual process, and in that step we identified that there is the highest chance of something going wrong, and I will explain a bit more later what are some main vulnerabilities there. The second layer is the front end, which has two main jobs. First is to get the circuit and compile it down to something that the proof system can work with. And the second is the witness generation process, which basically you get the circuit and your inputs and you generate a witness, which you can think of it as some trace for your computation. Here there can be some vulnerabilities. We didn't find many in our dataset, but for example, you can imagine in the process of compiling your circuit down to some intermediate representation like R1CS, if you do some optimizations, then you might have some misoptimizations and introduce some vulnerabilities. Next one, we have the backend, which is composed of the three main functions for a SNARK, which is the preprocessing or setup, the proving, and the verification. We identified a few bugs here, and most importantly, there are many SNARK verifier bugs, where basically the programmers do not implement the verifier correctly, and that can lead to the ability of exploiting even soundness vulnerabilities in the protocol. And finally, we have the integration layer, which is basically the layer that interacts with the prover, the verifier, and even the setup function in some protocols. In the blockchain world, you can think of it as a smart contract, or in another application, you can think of it as some client code that interacts with the ZKP. Or uses the ZKP. One kind of vulnerability that can happen here is that sometimes in the circuits we might have some implicit constraints, implicit assumptions that our inputs are fill elements, and we don't check about that in the circuit to reduce the number of constraints, so we have to do that check in the integration layer. One other important point here is that both the backend and the frontend are critical, and if any vulnerability is there, then it doesn't matter if our circuits are formally verified, they can still be exploited. Okay, so here are main results, and we notice that the most vulnerabilities are in the circuit layer, and most of them are soundness bugs, which is really bad. So why do we have so many vulnerabilities in the circuit layer? For mainly two reasons. First one is that the programming model is a bit different. because we have both computation, which you can think of it as the work that the prover has done, and constraints, which you can think of it as the work that the verifier has to do. And the two should match, and it's pretty complicated sometimes because you might want to do some optimizations, or you might want to implement some cryptographic primitives that are difficult to be described in a circuit. And in our paper, we have many vulnerability classes and root causes. Unfortunately, I don't have much time to go over them. But the main three patterns are the different programming model that is required for writing circuits, optimizations, and also cryptography being at the outer layer, and also some common mistakes like specification issues. Finally, in that table, we have all the different security tools that have been developed for ZKPs, and people have tried to use many different formal methods for finding vulnerabilities, mainly in the circuit layer. What we can see is that most tools focus on under-constrained bugs, which is the main category of vulnerabilities in the circuit layer. And also, what we notice is that most tools focus on a specific DSL or on a specific model of class of ZK DSLs, and they can handle only specific vulnerability classes. There are also some formal verification tools, but then we have scalability issues. Unfortunately, not much have been done in frontend and backend. In frontend, there's a real nice paper by Alex Osdimar about miscompilations, basically, when you try to go from your field down to your constraints. And also people have tried to use traditional security tools, but unfortunately it's pretty difficult to solve the Oracle problems when you use a traditional fuzzer, for example, to find that kind of vulnerabilities. So in conclusion, why do we have bugs? Unfortunately, although ZKPs are based on very nice maths, it's not just maths. Bugs in the implementation can break all the properties that zero-knowledge proofs provide. Another quote I want to use is one from Ron Rivest, which is that the poor user is given enough rope with which to hang himself. He wrote that in one of the specifications for digital signatures, but I think the situation here is even worse because we expose a lot of cryptography to the outer layers. We're missing fundamental abstractions in most of the ZK DSLs, and also we have a different threat model than traditional applications that might do the work of developers even worse. And finally, there is a lack of specification in that space, also in the application layer, but also in the front-end and in the back-end layers. So what can we do? Basically, we can negate all the previous ones, and then we might have a bit more secure implementations of SNARKs in practice. That was it, and here you can find the paper, and in the paper we have a link to a dataset with all the vulnerabilities we analyzed and our taxonomy. Thank you.